In this problem, we have a ladder that's being propped up against the side of a wall, and we're asked to find the force of friction that the driveway exerts on the bottom of the ladder. Now, there's a number of different ways to approach this problem, but we're going to approach it using torque. And so what's going on here is we have a bunch of forces acting on this ladder, and each one of these forces is exerting its own individual torque on the ladder. Now the thing is, this ladder is not rotating at all, it's stationary, so we know that the ladder is in rotational equilibrium. And because it's in rotational equilibrium, that means that the sum of all the torques caused by these forces has to add up to 0. So now the first thing we're going to want to do is we want to identify all these forces that are acting on the ladder.
Okay, so I'm going to redraw the ladder a little bit bigger over here. And so what we're going to do now is identify the forces acting on the ladder. And so the first force we're going to look at is the weight of the ladder itself. So there's going to be some gravitational force being exerted on the ladder due to its weight. And that force is going to look something like this. And it's going to be applied at the center of the ladder, so the center of mass of the ladder, because we're talking about weight. Now, for our second force, we're going to look at the painter. So the painter is sitting on top of the ladder at this point right here, and just like with the ladder, there's going to be some weight associated with the painter pulling the ladder downwards. So this is the weight of the painter, and it's acting on the ladder at this point right here. And now for the next force, we're going to move to the top of the ladder. And so we're going to look at the point of contact between the top of the ladder and the wall. And if you look closely, you'll notice that the wall is actually pushing on the ladder. And so because the wall is pushing on the ladder, it's exerting a normal force, horizontal direction to the left on the ladder. So we have a normal force up here as well. Now we're going to move all the way down to the bottom of the ladder. So if you look at the driveway, you'll notice that the driveway is also exerting a normal force on the ladder, except that this time the normal force is pointed upwards. So driveway is essentially pushing up on the bottom of the ladder. So that's another normal force that we're going to have to take into account. So that's the normal force of the driveway. The last force is a little bit trickier to spot, but it's going to be the force of friction that's keeping the bottom of the ladder from sliding. And so that frictional force is going to look something like this. And the best way to visualize this frictional force is, imagine if there was no friction at the bottom of the ladder. And this ladder would just slide and fall over. So this frictional force is what's keeping this ladder from sliding. So these are all the forces that we're going to have to consider when doing this problem.
So now that we've identified our forces, we're going to want to choose the axis of rotation around which these torques are acting on our ladder. And recall that we can ignore any torques that are acting on whatever point we choose as our axis of rotation. So for example, if we choose this point right here as our axis of rotation, then we can ignore the torque caused by the weight of the ladder. On a similar note, if we choose this point right here as our axis of rotation, we can ignore the torque caused by the gravitational force on the painter, which is right here. And then similarly, if we choose this point right here as our axis of rotation, we can ignore the normal force that the wall exerts on the ladder. Now, if we look at this point down here, if we choose this point as our axis of rotation, we can actually ignore two forces unlike with the other examples. Because at this point right here, we have both the normal force that the driveway is exerting that's pushing up on the ladder on, but we also have the frictional force here as well. So if we choose this point as our center of our axis of rotation, we can eliminate two forces instead of one. And so because of that, it would be best for us. It would be the most optimal path to pick this point down here as our axis of rotation as opposed to the other three, because that ways we can simplify this problem so we only have to deal with 3 torques as opposed to 4. Now that we've chosen our axis of rotation, I'm going to minimize this right here. I'm going to redraw this diagram. So this is the same diagram as before, except we don't have the other 3 forces crossed out. And so because our green dot is our axis of rotation, we can erase these 2 forces and we can take those out of the picture. So this green dot right here, this is our axis of rotation. Okay, so before I move on with this problem, I actually want to take a closer look at the actual dimensions of the ladder itself. So here we have the ladder, and this is the wall. So throw in the driveway, just for fun. And so we're given in the question stem that the length of the ladder is 5 meters, and that the ladder sits at a height of 4.7 meters. Now, one thing we're going to have to find before we move on with this question is the angle between the wall and the ladder. In order to do that, we're going to use the cosine function. So we're going to do a little bit of trigonometry. So we know that cosine of theta is equal to adjacent over hypotenuse. And in this case, our adjacent side is the wall, or the height of the ladder, so that's going to be equal to 4.7 meters. And our hypotenuse is just the length of the ladder, just 5 meters. So we write it up here. We have cosine theta equal 4.7 over 5. So in order to solve for theta, that's our angle is simply going to be equal to the inverse of cosine 4.7 over 5. And that value comes out to be 19.9 degrees. And so we know that this angle up here is 19.9 degrees. So now we're going to look at the torques that are being caused by the forces that are being exerted on our ladder. So I'm going to redraw the ladder right here. And so we know our axis of rotation is the bottom of the ladder at this point. So the first torque we're going to look at is the one that's caused by the weight of the ladder. So we're going to look at the torque that's caused by this force vector right here. It's the gravitational force acting on the ladder. Okay, so now recall that the formula for torque is equal to radius times force sine theta. Now the first thing we're going to look at is this radius variable right here. So radius is essentially the distance between the point at which
our forces acting on the ladder, and the axis of rotation. So radius is basically just the distance between the two dots on our diagram right here. And that distance here is 2.5 meters because gravity acts on the center of mass of an object. And so in this case, the weight of the ladder is acting on the center of the ladder. And so we know that the ladder is 5 meters. And so the distance between one end of the ladder, which is the axis of rotation, the center of the ladder, is going to be half the length of the total of 5 meters. So it's 2.5 meters. And so we can plug that value into R right here. Now we're given that the weight of the ladder is 120 newtons. Now as for this theta right here, so theta is basically just going to be the angle between our force and radius. So theta in this case is going to be this angle right here. And this angle here is actually going to be equivalent to the value that we calculated down here. It's going to be 19.9 degrees. So we can plug that value into theta. And plugging all these values in, we end up with a torque caused by the weight of the ladder of negative 102.1 newtons. This is a negative value right here because this torque causes a clockwise rotation, and recall that clockwise rotations, or torques that cause clockwise rotations, are always assigned a negative sign, whereas those that cause a counterclockwise rotation are assigned a positive sign. Okay, so now let's look at the torque that's caused by the weight of the painter. So here I'm going to redraw the same ladder as before. So we know that the axis of rotation is down here, and our painter is standing on around this point of the ladder. He's standing at a height of 3 meters. We also know the angle between the ladder and the y-axis, which we calculated before, to be 19.9 degrees. So in order to find the torque caused by the weight of the painter, we're going to use the same formula we did for the torque of the ladder, which is just going to be torque of the painter is equal to radius times force sine theta. Now the force is simply going to be the weight of the painter, which we're given to be 680 newtons. The angle is just going to be that 19.9 degrees. As for the radius, that's something we're going to have to calculate. So the radius, again, is just the distance between the painter and the axis of rotation. So it's essentially just this length right here. In order to find this length, we're going to do a little bit of simple trigonometry. So recall that cosine 19.9 degrees is equal to adjacent, the adjacent side, which in this case is going to be that 3 meters, divided by the hypotenuse, which is our radius. And then rearranging this equation a little bit, we get the radius to be equal to 3 meters divided by cosine of 19.9 degrees. That value ends up being 3.19 meters. So our radius distance between painter and axis of rotation is 3.19 meters. And we're going to plug that value into R right here. So plugging all those values in, we end up getting a torque of negative 738.35 Newton meters. And again, this value is negative because this torque is causing a clockwise rotation. So now we're going to calculate the torque that's caused by the normal force at the top of the ladder. Okay, so we know that our ladder is in rotational equilibrium, and what that means is that the sum of all the torques acting on the ladder have to add up to 0. And so the torques that are acting on our ladder include the weight of the ladder, the torque from the weight of the ladder, torque from the weight of the painter, and finally the torque from the normal force at the top of the ladder. So these three torques have to cancel one another out. And so we're going to plug in these values that we calculated for the torque of the ladder in here. And doing that, we end up getting this equation. Should be Newton meters up here as well. So notice that the signs for both of these torques are negative. That's because they're both rotating the ladder in the same direction and in the clockwise direction. So whenever we have a clockwise rotation, we treat that as, we assign that torque a negative sign. So these two plus the torque caused by the normal force have to add up to 0. So rearranging this equation, we get the torque caused by the normal force to be equal to positive 102.1 Newton meter plus 738.35 Newton meter. So the torque caused by the normal force at the top of the ladder comes out to be positive 840.45 Newton meter. And notice that this is a positive torque. That's because the normal force is pushing the ladder in the opposite direction that the weight was. And so the normal force is causing a counterclockwise rotation. So whenever we have a counterclockwise rotation, we treat that as positive as opposed to negative. So now we're going to solve for the actual magnitude of the normal force that's been exerted at the top of the ladder. So we just solved for the torque caused by that normal force, but now we actually want to ask ourselves what that normal force is. So I'm going to redraw the ladder, and we have our axis of rotation down here. So the normal force is acting at the top of the ladder, and it's acting in the negative x direction. So that's the normal force. And so we're going to use the same torque formula we've been using this entire time. So torque caused by the normal force is equal to radius times the force, the normal force. So this is what we're trying to find right now, times sine theta. So the radius, again, is just the distance between the normal force and the axis of rotation, and that's just going to be the length of the ladder, which is 5 meters. Now for the torque caused by a normal force, we just calculated that, and that comes out to be 840.45 Newton meters. So the thing we have to solve for now is this theta right here. So recall that theta is the angle between the force and the ladder. And so in this case, our theta is going to be this angle right here. Now I'm going to draw in the wall that this ladder is propped up against. And recall that the angle between the ladder and the wall is 19.9 degrees. Because the ladder and the normal force are perpendicular to one another, if I extend the normal force line out here, so because they're perpendicular to one another, they form a 90-degree angle. And because it's a 90-degree angle, that means that our theta, this angle right here, is simply just going to be equal to 90 degrees minus 19.9. That ends up being 70.1 degrees. So we can plug 70.1 degrees into our theta over here. And now solving for the normal force, or F, we end up getting 840.45 divided by 5 meters times sine 70.1 degrees. So our normal force at the top of the ladder is going to be equal to 178.8 newtons. So if we just round that, we can just round it to 180 newtons. Now this force is actually equal to the force of friction that the driveway is exerting on the bottom of the ladder. So this is actually our final answer. And the reason why those two forces are equal is because so I'm actually going to repost the diagram with all the forces drawn in. So here we have the ladder with all of our forces. And so let's look at this from a translational motion perspective. So translationally, more specifically, let's actually look at only the forces acting on the ladder in the x direction. So we can ignore all the forces in the y direction, so I'm just going to go ahead and erase all of those. So the only two forces we have acting on the ladder in the x direction are the normal force at the top of the ladder and the frictional force at the bottom of the ladder that we're trying to find. And because this ladder is stationary and not moving in the x direction, that means that the sum of the forces, the net force in the x direction, have to add up to 0. And the only two forces, again, in the x direction are the frictional force plus the normal force. So these two have to add up to 0. So that means that the frictional force is equal in magnitude to the normal force caused by the wall. The only difference is those two forces are acting in opposite directions. So they're equal and opposite. So what this means is that the magnitude of our frictional force is 180 newtons. Now what's the direction that this frictional force is acting in? Well, the normal force caused by the wall is pushing the ladder to the left. And because the ladder is not moving at all in the x direction, that would mean that the frictional force would have to counteract that push. So the frictional force is going to be directed towards the wall to the right. So that's the direction that the frictional force is acting in. So it's going to be to the right at a magnitude of 180 newtons. And another way you can think of this is, say we have our ladder here, and we have the wall, our driveway. Now, if there were no frictional force at this point down here, if we didn't have any friction, this ladder would slide to the left. So what the frictional force is doing is it's providing a force towards the wall to prevent the ladder from sliding. So the force has to be directed towards the wall in order to prevent the ladder from sliding away from the wall. So in summary, our frictional force has a magnitude of 180 newtons, and it's directed towards the wall. And that is our final answer.